Petralanda. He made his PhD thesis in the University of the Basque Country with Professor Íñigo Echevarría, studying phase transitions in ferroelectrics in the framework of Landau theory. And he did a short postdoctoral stay also in the electrics in the Institute of Physics in the Czech Academy of Science. Then he has moved to the Italian Institute of Technology on a postdoc position for quantum materials theory group, and later in the nanochemistry group, later in the same institution. And then he has come to Denmark, to the computational atomic scale design section, with some people known here, like Professor Thomas Olsen in the Technical University of Denmark. And now is Maria Zambrano Fellow at the University of the Basque Country. So please welcome. You have something like 40 minutes to 45 maximum to talk, and left some time for discussion. Please go ahead.
So thanks, Andrés, for the kind introduction and for the invitation too. Thanks for everyone who's here attending the talk. So as Andrés mentioned, the talk today will be about ferroelectrics, in particular 2D ferroelectrics, and in particular domain walls that arise in this type of material. So the topic is pretty concrete. It will be based on one work that we did lately. So it's going to be pretty specific. So if you don't mind, I will spend one slide to talk about my previous work and try to find maybe if there are some overlapping interests with people with the group. So my work has been mainly split into two branches, which of course interact, which of course overlap with each other. One has been like ferroelectrics, and the other one is nanomaterials. In ferroelectrics, the first subsection somehow is the Landau theory of phase transitions that I worked during my PhD. And then I started to do some domain walls in the early stage of my postdoc time. And also then after some couple of years of not working too much on ferroelectrics, I returned to domain walls again in the last couple of years in Denmark. The other branch would be nanomaterials, especially in those 3 years that I mentioned during my postdoc time in Italy, in Genova. I was in Libromana's group, where we did basically light emission in nanocrystals and cation exchange. There was a heavy collaboration time with computation with experimentalists at that time. And also just to mention that these books, I did some high throughput studies in 2D materials in this last postdoc in Denmark too, in the CAMD and the CAMD section of the Department of Physics. So today, as I mentioned, it will be just basically, it will be, okay, this is the pointer. The talk will be about this work here. The title is not here, but it's basically our polarization solution to the ferroelectrics. And also we studied some optical properties of domain walls. And just in case, although in the audience, I think there are real experts there are experts in ferroelectrics too, but I will try to give a kind of an overview of ferroelectrics first, and then introduce you to that, and then try to delve deeper into the topic. So, I think everyone has had in his hands a magnet, right? Every kid or most of us have had a magnet in our hands, and then we start in contact. We get into contact with physics, with fields, magnetic field, electric field. It is very natural to understand that a material can have an inherent magnetic field because we have had it in the hands, we have touched it, and somehow it becomes like a natural thing to think of. In fact, if I go to Google and I write a magnet, the first images I'm getting are things like this. They are objects that, they are dirty, they have been around, and they have fallen down somehow. We know that they're incorporated in our culture, and we see them every day. However, if I write ferroelectric in Google, where I get these rather academic pictures all around, and that means that somehow we don't see them every day, even if they are the natural extension, the natural analogous to magnetic materials, because they have an electric field embedded in there. in the crystal. But they actually do exist. They're actually applied. They are applied in ferroelectric memories, in switching devices. I think it's basically, I'm not a real expert in this, but I think they are applied quite a lot in hard drives and so on. And people are considering to actually make a big transition to ferroelectrics because they have some advantageous properties versus semiconductors in some senses. So this being said, like 5-6 years ago, there was the first synthesis of a 2D ferroelectric material, a monolayer ferroelectric material. And since then, there have been some more compounds appearing. Not a lot. There are like a dozen, but still, it has been really vastly studied computationally because it has a lot of they have a lot of promise. In what do they have promise? So they have certainly applications as capacitors in energy storage materials. They think they can be used also as photovoltaics. And here I can say that one of the ways to harvest light in photovoltaics is non-linear responsive materials. And here, I think in the center, there are world-leading experts in this topic. And something else that these ferroelectrics are, the materials that happen to be ferroelectrics in the monolayer shape, like monochalcogenide, for example, they have also believed to be good thermoelectrics, which also can link to other anharmonic experts that you have here in the anharmonic effect experts that you have here in the center. So once after introducing what role ferroelectrics play in our everyday life, let's go a little bit into the science. So materials that have intrinsic magnetic electric field don't need any conditional electronic from their electronic structure. The only thing they need is to present a polar space group. So it's a totally structural feature. And many space groups are polar, actually. Out of the 230 space groups, about, I don't know the number, but like 20-25% of space groups are polar. And all materials belonging to those classes, they are pyroelectrics. Why do we call them pyroelectrics? Perhaps it's a historical reason because temperature, for example, which is the most common environmental variable we can think of, will change in general the atomic position of materials, and this atomic position change, of course, will change the intrinsic dipole moment of the crystal, and then we can detect the changes of temperature through changes of the intrinsic dipole moment of the material. That is why the name pyro comes, probably. And out of all these polar materials, that we can say there is a subclass, which is called ferroelectrics, which is defined by having a polarization, a spontaneous polarization, which is switchable under an applied electric field. And why does this happen? Well, it's quite intuitive because we have like an intrinsic spontaneous polarization on a material, and we have an electric field that opposes it. And the energy term that will be relevant from this is the minus E scalar P. So if E and P are opposite direction, the energy will be positive. So that will be penalized. So then the system will always try to flip this arrow to the other side and try to align with the electric field. Of course, some materials, before this happens, in some materials, the electrons in the valence band will, due to the linear potential introduced by the field, will travel to the conduction band. This will destroy the gap. This will create a screening of the electric field by the electrons. So then the ions will not feel the force to switch, and then they will return back to their initial positions. They will not be able to complete the switching. So all these materials that don't lay here, that's why they are separated and they lie in the ferroelectric category. And one thing that is particular to ferroelectric that wouldn't necessarily be there is like an associated centrosymmetric phase of a ferroelectric material. And it's important, at least for two very important things, but it's important because of the two reasons. One is the calculation of the spontaneous polarization can only be done in relation to a centrosymmetric phase. And the second is that ferroelectrics normally arise after a cooling from a centrosymmetric parent phase. So there's a phase transition that gives rise to ferroelectrics. And in fact, domain walls are understood the best in the context of a phase transition. So let's look at phase transitions. As we all know, a system will always tend to the minimum of the appropriate thermodynamic potential in a given environment. The simplest thing we can think is just temperature, right? So we can write the free energy in terms of the internal variables of the system and putting it on the temperature. So if we're going to calculate it formally, we have to use statistical mechanics, and we can do calculations with that. Free energy at zero temperature matches the internal energy that we can calculate by DFT. But of course, calculating the renormalization of the free energy is not an easy thing. It's non-trivial and requires sophisticated approaches. So let's say a tool that the Landau theory of phase transitions is built in order to simplify greatly this type of problem. The most important concept is it's a quantity called order parameter. Just marks the progression, which marks the progression of the phase transition going from 0 to 1. And what is done is to ad hoc build a functional shape of the free energy that will have the properties that reproduce a phase transition. So the free energy has to be in the centrosymmetric phase, has to have a minimum when the order parameter is 0. In our case, when the system is centrosymmetric. And then when T value is lower, it has to fulfill the condition that the order parameter is 1, basically. And also has to be symmetric because of the centrosymmetry of the parent phase. And we see it visually here that when the system is here and we have a centrosymmetric phase, there is only one minimum of the free energy. But once we cool it, we have two equivalent minima of the free energy. And this has a very important meaning because in a crystal, you will have equal right. There will be an equal probability of so that a section of the crystal presents this order parameter or this order parameter. So what is the solution that the crystal finds? The crystal finds the solution of breaking down the crystal into different domains where they have different orientation of the order parameter. And on the boundaries of these domains, that is where domain walls arise. They have different properties, different electronic properties, different structural properties. So now that we know how domain walls appear, let's see some real images. No? So this is barium titanate. You have the red arrows pointing at different directions of polarization. In fact, in these yellow lines indicate the domain walls. You see, they are not perfect. But for example, this domain wall could be 90-degree domain wall, schematized here. I don't know. Yes, these are mostly 90-degree domain walls. But yes, this, I guess, if there's a boundary between these two arrows, at some point, this will be a 180 domain wall. So there's a kind of a lot of diversity, right? A lot of an ecosystem of domain walls appearing all around. And domain walls have been simulated for a long time, even DFT. I mean, people have been doing DFT from the starting of the century, from the start of the century. And then they have done also, people have done phase field simulations for larger systems and so on. I just showed you a picture of one of our works. The particularity of this work is that, the arrows are pointing, the normal component of polarization is changing across the domain wall, meaning that there is a bound charge that accumulates at the domain wall. And this bound charge accumulation, actually, the system tries to compensate and tries to create free charge. And you get like a two-dimensional electron gas embedded into a ferroelectric that you can use for many applications and so on. But after this introduction, where we are concerned about is two materials in this case. So let's jump into that. So there, as I said, not many monolayer ferroelectrics existing, synthesized by so far. In this family of monochalcogenides, there are two, as far as I know, in the very monolayer limit. We have tin telluride, which was the first 6 years ago, synthesized. And then we have tin selenide as well. Then there are a few layers ferroelectrics too. So I think it will be a matter of time to get more members of the family synthesized. And they actually see domain walls there. So this is a 180 domain wall in tin selenide, for example, in this tool. Then we have 90-degree domain walls in tin telluride. So domain walls are prominent in experiments. Indeed, the very proof of having a ferroelectric is having the domain walls. They use the fact that they see domain walls to justify that they have actually a ferroelectric, a ferrite material. So they are there. They influence the properties of the material. They do. They influence the properties of the material globally, and they also have by themselves interesting properties. So they can be used for. Actually, there are prospects of using these domain walls as building blocks of neuromorphic devices and all type of very advanced concepts of switching devices. So what did we actually do? We started to construct the domain walls, right? So the 180 case, I think it's quite a straightforward case. We have the unit cell of the material, let's call it A and B. And we define the anisotropy of the material by taking into account these two lattice parameters. And then we have a polarization of pointing, sorry, I should have removed this P, pointing in X direction as we see. So to build the domain walls, the only thing we do is just to flip it 90 degrees, put several unit cells together here, then flip it down and put all the unit cells together on the other side. Normally we use larger domain walls so that we minimize the domain wall interaction between them. And then we just relax and calculate and see what happens. And to construct the 90-degree domain walls, well, it's a bit trickier. One has to do a little bit of trigonometry here, but it's also not too complicated. We have to put four unit cells together, and across the diagonals, we can form the small supercell that we call rhombus unit cell. And then using this building block, we will be able to build the 90-degree domain walls. This tilt here, this is not flat, and this tilt that we see here is due to the difference between B and A. If B and A were the same, this would be just squares, and we will have just a rectangle. So going into the technical details, of our calculations, I think it's worth saying that there were. We did some convergence tests first to see what size of domain walls we needed and so on. And when we took 90-degree domain walls, that was very smooth. There was no strain appearing upon relaxation, and we could just see that the domain wall doesn't really disrupt the structure too much. However, the 180-degree domain wall, in the case of the most anisotropic material, which is germanium sulfide, the stress in the relaxation was really huge. So we had really a big value of the strain, of the lattice strain once we relaxed. And actually, we didn't recover the bulk polarization far from the walls. So it was clearly not reproducing the right system. So what we did was to fix this lateral cell parameter of the supercell and relaxed. And then we also got rid of most of the stress in this direction. So we could just, that's how we kind of, so that is the constraint we adopted in order to study 180 domain walls, as opposed to the 90-degree domain walls. That was just a relaxation allowed for everything. And well, now I show some results, some numerical results. I think we don't need to go to all the details of the numbers, but essentially the thing is that as the anisotropy is increased, we see that the walls are sharper and thinner. They are less stable, and they are more rigid. It's more difficult to move them around. And then this means that we can actually predict, in principle, not predict exactly, but we can have a real clue of how the domain wall will be just from the bulk structure itself, because we can just take the lattice parameters of the bulk, and then we can imagine what properties the domain wall will have. And it gives a clue. It's not exact, but it's a clue. Then we went to electronic properties, because after having the structural properties, we tried to study the the band structure. This is a 90-degree domain wall. We studied the path in the Brillouin zone that is perpendicular to the wall, to the domain wall, and we see how it influences the electron properties. So we see that actually the states are not too localized. You know, this is high localization. So 1.0 would mean that the band is 1.0. A yellow band would mean that all the states live only at the domain wall. So we see quite it's pretty spread all around. It's not really, we don't see a real impact. A real 90-degree domain walls don't really, exert a very high influence on the electronic structure of the material. And then we say, so let's see what happens with absorption of the material. And put in a high density of domain walls, because doing RPA with very large supercell is memory-wise very, very expensive. So we try to put a smaller supercell, so higher domain wall densities, but try to calculate which is the absorption of for example, comparing the domain system with many domain walls versus system versus bulk, and for two compounds. And we saw that the changes, there are some changes, but not too much. No, it's pretty much consistent with the fact that 90 degrees are smooth in the material. So then we jump to 90 to 180 domain walls, and so what would happen. And in fact, this is a totally different picture. The lowest band in the conduction band is nearly fully localized at the domain wall, and actually comes down pretty much from the conduction band. In fact, thus decreasing the band gap of the material. And this manifests clearly in the absorption of in the absorption picture. The onset of the absorption move left. There is a red shift of the absorption peak, and that means the material is absorbing more light in the lower energy range and less light in the high energy range when there is a domain wall involved. So what does it mean? This could be, this has of course limitations, because for this process there are excited states in reality taking place, and one cannot do GW for very heavy systems. So the calculations have their limitations, and also this is obtained when they are like 12 angstrom, 15 angstrom different distance between domain walls, which I guess experimentally is not easy to achieve. But in any case, this is telling us that at high densities of anisotropic domain walls, the gain in the absorbance in the solar spectrum is increasing. So if people want to apply this type of compounds for solar cells, domain walls at least are not hurting. So one doesn't have to get rid of them in the synthesis process or in the fabrication process. In any case, they are helping, which is something we didn't know and we didn't expect. Came out. And maybe the main thing we studied here was the polarization switching behavior of the material, because ferroelectric materials have prospects of being applied in many fields, but where they are really more relevant, as far as I know, is the switching of polarization. You have chips and so on, where you apply a field, you change the polarization, and you use that as a 1-0 type of chip type of thing. You know? So the main thing here is if we apply polarization on a ferroelectric, or we apply a field on a ferroelectric, how is the polarization going to change? How is it going to shift? Which is the pathway of shifting. So one option is we have a large polarization pointing left, we apply a field pointing right, and slowly the whole crystal just moves from the energy minimum to the centrosymmetric state, and then continues until the new ferroelectric energy equivalent state to this in a collective type of movement. This is one option. And the other option is there are domain walls, there are domains in the crystal, initially in the crystal, and the electric field pushes the domain front forward in the material until it finally reaches the end. So what was yellow in the beginning becomes purple in the end. So there are two mechanisms, two very distinctive mechanisms that one has to know to really understand what's going on in the chip. Right? So one has to see if what is the real driving mechanism in the material. So to understand this, we studied the switching, because this thing, this is already calculated for all the materials. But about domain wall propagation, very little is known actually in the literature, not even in 3D, as far as I know. Maybe people in the audience can correct me, but I think not even in 3D. There's a lot of knowledge of how to treat this. So what we first did was to calculate the energies, right? So we went to first, let's take a 90-degree domain wall. We set up a configuration with a domain wall in the middle, if you want, and its periodic image, of course, in the edge of the supercell. Let's not forget it. And we just displaced that domain wall one unit cell, right? Both the center domain wall and the one in the edge that goes on the other side, and they'll do an edge elastic band between the two states. As you know, the edge elastic band give us the path of the minimum energy path to reach one state starting from the other state. And what we found for this is germanium sulfide in particular, but we have done it for all materials. What we found is that there is two peaks, two symmetric peaks, because the system in the middle is energetically equivalent to the system in the beginning. So from here to here, there's only half a unit cell displacements, and from here to here, another half, right? So one can actually exploit these symmetry requirements to make the calculation much cheaper, much faster. So we saw that the germanium sulfide, again, the most anisotropic compound, is the most difficult to move. Like it's very, very abrupt in the material, and it's very unstable and also very difficult to move around. However, in the less anisotropic materials, which are actually the experimentally existing materials, we have this. This is experimentally existing as a monolayer, and tin telluride is also experimentally very existing. So their barrier is near zero. It's very small. Here, as a comparison, this is lead titanate, calculated 20 years ago, something by Vanderbilt and so on and company, which is higher, much higher than the tin selenide. And then we went to 180, see what happens, and a pretty similar picture. We have the anisotropic compound is the most hard to move, which is this time on the order of magnitude of lead titanate, and the most less anisotropic systems have like 2 orders of magnitude lower energy barriers. So then this tells us something, right? So the energy barrier, I forgot to say that the uniform coherent switching I mentioned before in the picture, it's very similar to this one. I don't show it here, maybe I should show it, but the coherent switch and energy maximum is more or less the same magnitude as this. So if we take that high value of the coherent switching and then go to germanium selenide, which is here, it's very clear that the system will prefer to slide the domain wall, which is 2 orders of magnitude cheaper than moving the whole material from one side to the other. So from here, we think we can conclude that for low anisotropic materials, at least for the experimentally existing materials, tin selenide, tin telluride, the polarization switching happens through domain wall propagation and not through coherent switching. But in reality, to compare it, to have a numerical value to compare to the experiment, in the experiment, it's not typically, you will not see typically the energy barriers. What you will work with in general will be the electric fields, and you will have a coercive field after which you can really switch polarization and switch it back. So it's the language somehow is coercive fields, electric fields. So this coercive field is the field where there is where after which the system switches actually. So what we did, which I think was to forget the bulk, the coherent part of the domain of the ferroelectric switch. We just forgot that. We just thought about a domain wall propagating. So we wrote a free energy as a function of this domain wall propagation. Okay. This energy is obtained. This is the internal energy obtained by this is an electrical. To put it in thermodynamic language, one could also write the energy here and call this ab initio energy of zero, and then call this minus EP. But I don't know. I feel it's more natural to talk about enthalpies. But this, I think, arbitrary. So this is the calculation by the ground calculation by DFT. This is the dipole moment of the system, which is related to spontaneous polarization, and this is the electric field of the system. This is the electric enthalpy. So one can actually write this into taking that into consideration that the relevant direction of the electric field will always be parallel to the polarization, and we can neglect wherever the components of the field that are perpendicular to the polarization, and write the enthalpy in a simplified way. There's only with only one direction, and use actually the natural elastic band as the energy path that the system will cross. So we are crossing. Let me go back a little bit. So we are crossing this path, and we are actually trying to see which is the slope, the maximum slope here that we need to apply the field, so that if you apply a field that overcomes this slope, the system will automatically go to the other side. Okay. So we're just trying to find this slope. The thing is that people in general, I think, they were trying to use, this Landau-Ginzburg model where the gradient of the polarization is used to describe the domain walls. So I think the main thing is to just forget about the path, take the domain wall movement, and write the electric enthalpy according to that. And well, this is the expression we got for the coercive field. And what we did was just to calculate it. So we took all four materials in the two domain wall configurations. So it's 8 configurations in total, and try to calculate the coercive fields that we were getting. So unfortunately, yet there's not a lot of evidence about this, but luckily there is one experimental point, which is actually this, which is for few layer tin sulfide, 9 layers, I think. They have measured the coercive field, and it's 22 kilovolt per centimeter. However, the coherent switching, the electric field, coercive field derived from the coherent switching energy curve gives you 2 orders of magnitude larger value of the coercive field. So there's something wrong with that. And in our simulations, actually, seeing which is the energy barrier of the domain wall propagation, we get 5.3, which is at the same order of magnitude as the measured electric field. We have to take into account this is 9 layers in only one monolayer. It could probably match better, but there could also be some point defects stopping the domain wall, or other type of things stopping the domain wall in the experiment. But being in the lower range, I think is positive, because the only thing the defects will in general do is slow it down. So we believe we have kind of solved like inconsistency between experiment and calculation in this sense. And we are of course waiting for other materials to be synthesized. This one exists, but I didn't find any values for the coercive field. But waiting for people to synthesize more materials of this family and try to measure these fields and see if it's actually the domain wall enthalpy that really matters for the switching. And I don't think I have too much more. So to say, let's read the conclusions. So this lattice anisotropy really influencing the structure and stability of domain walls, both types. 90-degree domain walls always more smooth than 180-degree domain walls in all cases. Then electronic structure, nothing special in 90-degree domain walls. However, localized states in the domain wall localized states for 180 domain walls, and decrease of the band gap. Decrease of the band gap brings a redshift of the light absorption, which is positive for solar applications, because in fact the absorption peak is a little bit blue shifted than ideal. So bringing the red is good, but of course this will be very difficult to check, because of course it's you cannot gather so many domain walls together, and who knows. In any case, the domain walls are not hurting the solar applications. This is at least one take-home message. Ultra low energy barriers for domain wall propagation, except for germanium sulfide, the most anisotropic material. But at least for experimentally existing materials, probably the proof that the polarization switching happens through domain world propagation and not coherent switching. And yeah, with this, maybe I don't know if it was too fast, but I want to acknowledge people at CAMD for this, because for this work we did of domain worlds into the Ferroelectrics at DTU, especially Professor Thomas Olsen that I worked with. And of course, thanks to you all for coming here and for your attention. So.
Thank you very much for the excellent timing. So there are questions, comments, yes, please.
Sorry, maybe you said at the beginning, but they came a few minutes later. I wanted to know, what is the transition temperature of these materials?
Of these 2D materials?
Yes, for the...
I actually don't even know if they have a centrosymmetric phase that is known before it melts.
But the temperature...
I'm not really sure. I really don't know. I would say, I think I don't want to give a number because I may be totally wrong. So I would possibly refrain from answering. But not room temperature, they are ferroelectric, that's for sure.
No, of course, yes.
It's higher. I mean, it could be that they, it cools down, and because some ferroelectrics exist.
Well, the calculations you made are at the low temperature, 0 temperature.
Technically, yes, I mean, sure, but the same structure that is at 0, sort of, let's say, prevails at room temperature.
Ah, okay. So at room temperature, they are ferroelectrics then. Okay.
Any more questions, comments? Yes, please.
Yeah, I've been following a bit this type of research, this line of research, and I remember there were some papers discussing the transition temperature into the ferroelectrics, especially I think tin telluride with selenide, and doing Monte Carlo simulation on that's fitted to the DFT results. And what they have found, if I'm remembering correctly, is that the transition temperature in 2D is higher than in 3D.
Yes.
Especially that's already seen by the tin telluride in 2D being ferroelectric at room temperature, while it's paraelectric at the room temperature in 3D. I wonder if you have any intuitive explanation why is that? Because if you look at the icing model, it's the other way around. The icing model has a lower transition temperature in 2D rather than 3D. And the interaction that drives the phase transition should be quite similar in both cases. So yeah, that's my question. Whether do you have any intuitive reasoning why these 2D ferroelectrics would be more stable?
If I have to say something, I think in the icing model, the dimensionality of the order parameters matters for the fluctuations of the order parameter. So perhaps it is when the order parameters has more dimensions that it will fluctuate more when in high temperatures. So the model may transit earlier to in a lower temperature. And here, maybe the surface effects, the fact that you're exposed to a vacuum somehow, maybe prevents the other atoms from influencing the atoms in the monolayer, so that somehow, how would I say, the fact that there's nothing there, if you have many atoms that maybe they're moving around, and the monolayer would also feel it, and there would be a transition somehow. But if there's no other atom moving around, I don't know, just heat wise, we don't know how to view it if not in that direction. The influence of the surrounding atoms, if you want. In the icing model thing, I think it's related to the dimensionality of the other parameters. I think it's related.
May I have a comment on this?
But in the real material side, that's what I would.
I'd like to add a comment because, as you mentioned, these problems have been studied already, I think 40 years ago, these problems. And I remember that for perovskites, layered perovskites, like for example, I think potassium selenate was one of the cases in which temperature was higher, as you mentioned, and then in other cubic perovskites. And this was actually connected because at that time the critical exponents had been measured. And the question was whether the transition is first order or second order, namely supported by a soft mode. And mostly are second order. And the question was whether it, two-dimensionality. And this was connected because at that time the critical exponents had been measured by Alex Müller. And Alex Müller got the inspiration to move to perovskites, layered perovskites for the superconductivity, because there was a connection due to the electron-photon interaction, which was actually producing this. So this is very interesting comment on importance of two-dimensionality. Yeah.
Mm-hmm. Please, John.
So Urko, it's a pleasure to have you here. Very nice talk. I have a question. So if your order parameter, let's say if it's normally a phonon mode or it's a displacement vector, right? Or it's a phonon eigenvector.
Yeah.
If it is degenerate, so instead of having like a double well, you might have like a Mexican hat-like thing, right? So maybe by symmetry, it's not given that all the points give you the same energy. So what happens in these cases with the domain walls? So you have like a more variety of domain walls, very different, or?
Exactly. By having more multiple energy equivalent wells, like it happens, for example, in lithium manganate, where we have a Mexican hat, as you said, there are 6 equivalent energy minima. So typically domain walls, instead of being 180 degree, will be 120 degree, 60 degree. Mm-hmm. So they will kind of respect this symmetry of the crystal. So the polarization, instead of moving, the angle of the domain wall, I think I didn't mention this actually. The angle of the domain wall is determined by the change the polarization vector does across the domain wall. So that's why this is 90 and this is 180. So if we have let's say 6 equivalent minima, probably we'll have polarization pointing, let's say this can have 0. If we take the vertical, for example, as a reference, and there's a domain here, so the polarization direction is 0 degrees, and the next will be 60 degrees, right? So maybe in the boundary between these two domains, the polarization will be 60. Domain wall will be 60 degree domain wall, for example, or 180 or whatever it is.
Please, no comment in the chat. Further comments by the audience? Daniel?
Yeah, I have just a technical question. When you do your DFT calculation, do you have to take a special care with like using some cutoff for Coulomb interactions or something to treat really 2D materials? Is that important, or simply taking big distances is enough?
Well, ideally one should do, I guess, a convergence, and what happens is that in C2DB they have a lot of the C2DB is project a database they have where they have a lot of calculations of 2D materials, so where they have already done all the convergence tests. So I basically pick the materials from there and use the technical parameters from there directly. But of course, one should take care, and then one should be careful with these cutoffs. But I just used the domain wall. The domain wall itself didn't introduce any new, as far as I know, any new requirements.
I have a
Yes,
question.
please.
There was a slide where you had shown the localization of bands. I'm not sure I quite understand what it was. Could you repeat it, please? Exactly.
So, for example, we calculate the band structure, and then at each K point, we will calculate which is the projection, which is how much this state is localized into the domain wall in real space, in the atoms forming the domain wall.
Okay.
So that if the whole band is localized, if all the electronic, if there's the projection of the band into the projectors coming from the atoms living at the domain wall is 1, then it will be totally localized, and we will give it value number 1, value 10. And if it's totally delocalized, that will be lower values. So that will be the color code.
Thanks.
There you have like it's like 2 bands, no? Because also you have like one that is yellow, but there is one that is in between, no? It's like
that is true.
Still separated. So
that is true. Actually, in the literature, so this is done in another paper. And a similar calculation is done for germanium sulfide, not for 90-degree domain walls. But there's a seminal paper of 2D Ferroelectrics that actually does a similar calculation. And they do have a clearer band here, second. But we get this very localized, and this one is, well, localized, but not so much.
Half. I would say halfway.
Yeah.
Okay. This is seems very separated from the upper levels.
Yeah, that's why
like above levels already. So that's okay. Any questions, comments? Well, I have one. It's about in one of the last slides you saw this maximum field, the table.
Yeah.
The table. Here there is some values like tin selenide and so on, and there is some big changes. Now for 23 to almost, there is some reasons for this, like it's more like what's happening with the electronic density, or what is the?
Yeah, it's actually coming from the fact that the energy well is much deeper. So it's coming from the fact that this slope is huge, and this slope is nearly zero. So this actually, the values in the table are just equivalent to this. And it happens apparently because of the anisotropy. So it seems like the material is very anisotropic. So the wall is somehow, it's very uncomfortable for the material to put the wall there. So it becomes quite unstable and it doesn't move easily. So that's kind of the origin. It's a structural, I think it's just a structural feature. It's just a static.
I was thinking whether they have some sort of electronical origin, like something like the one has more, this kind of lobes are more localized, or there are less.
It has a manifest. I think that maybe that thing has a manifestation also in the electron structure. I would also bet that.
I don't know.
Definitely.
I found curious that the big change, and also whether this can be somehow linked to the bond between the two materials, whether you have germanium with tin or with selenide, or you just change it a little bit the kind of bond you have, because you are going up in the periodic table, and somehow you are getting sort of region where you have just above germanium you have silicon and so on. It's like when you go up, it's like more and more covalent bond. So then maybe there is sort of also anisotropy in the electronic density, and that makes also that this made the changes here when you are moving the atoms. But okay, we can discuss it later.
It's not really.
Okay. There is, yes.
Just a comment, because in tin selenide, so maybe answer it to Georgia and Georgia. We did a calculation of the transition temperature in the bulk that we published, and in the monolayer that was a side project that we never got it, we never published, and it was much lower in the monolayer. Yeah, it was according to the calculation. We are not so in our calculation we got it around 700 Kelvin for the bulk, and experimentally it's higher, it's 800. And in the monolayer we got like 200, no, a bit lower, 100 and something. But experimentally it's true what Urko says, that at room temperature still is in the ferroelectric phase. So it seems that we are underestimating the critical temperature, but it's lower for sure in the monolayer.
That's interesting.
Can this be due to the substrate? Yeah. The substrate has some.
Yeah,
could be, but I mean, in the bulk, we are also underestimating the transition temperature. So it might be exchange correlation effects, finite size effects that in the calculation we cannot really.
Normally the temperatures, magnetism, so then normally when you go below the dimensionality, always the temperature goes down. It's going up is like will be very, very unusual. So then,
well, there are claims that for charge density wave transitions that it goes up a lot in the monolayer limits. There are experimental claims about that. We don't believe it, but I mean, so okay. I just wanted to make this.
But the substrate certainly will have to play a role there, so like to fix some vibrational levels, so that and the strain that you put in these materials, because they have some strain already.
Yeah, I pointed that there are two ingredients. One is electrons and the other are phonons, because it's an electron phonon mechanism, and therefore that's why it's difficult. If you have substrate charge transfer and everything.
Sure.
and,
These effects, yes.
addition of complicated band structure. So there's no, you're right, there's no rule for that, just cases.
Yeah.
Okay, so if there are no further questions, let's thank the speaker again. And if anyone wants to talk to him, he's also open to discuss. Okay, see you. Thanks.
Another question. How sharp is the wall?
It's like a couple of units.
A couple of
Units.
yes. So
In
sharp.
calculation,
Fantastic.
Just
The other question was at the time the motion of the and the motion of the wall, but also the shape. It's the king, sort of king solid on it, which was
yes,
described as very interesting. I'm glad that electricity is reviving.
yeah, it's something's been known for a long time. Now actually established.
In fact, it's great. It's great. Well, can you isolate the road?
Yeah, it's totally known.
No friend.
I think it was good to have some national credits to have a reference about that.
Okay, thank you. It was nice to.
Yeah.